Cool. Alrighty. So, thanks for coming out at like fucking nothing o'clock. Uh, sorry, I only recently decided that I speak enough that I deserve a slide clicker, and this is life changing. Um, so anyway, my name's Richo. I do security engineering for a payments company called Stripe. I used to make lots of jokes that were pretty little and you've never heard of this, but they're starting to get bitterly ironic. Anyway, I'm here to talk about a tool called Voltron, which is a debugger implant for GDB and LDB, which I'll go into in more depth in a second. But in the name of full disclosure, I didn't write this tool. My friend Snare did, but then I went ahead and rewrote a couple of fairly significant components of it, as well as get really excited about some crazy bullshit that I could build on top of it, which I did, which now I'm going to show you. So yeah, it's not my tool, but I own a lot of the code in it now. A little bit of background about me. I grew up in Australia. I used to reverse engineer .NET. I built infrastructure for a while. Now I do security engineering. At various points I've broken things. Everyone always asks me how to pronounce my name, so I have this handy pronunciation guide in all of my slides now. It's like Richo. And I guess, like, given that there are so few people here, if what I'm saying isn't making sense or you have a question, like, just ask me. It's probably going to be easier to answer it halfway through than have me talk for 20 minutes about things that aren't making sense and then try and backfill. So anyway, like, why even use a debugger in the first place? Like, broadly, you can divide debuggers into two categories. So you have, like, static analysis tools like IDA, Hopper, Capstone, and dynamic debugging tools like GDB, LDB, Winbag, Ollie. In general, like the two main use cases for using a debugger is that you're interested in finding bugs for the purposes of exploiting them or finding bugs for the purposes of killing them. You can kind of use this tool for either of those things. My big demo, which we're going to see how this plays out when you have a 25-minute talk and organize a 23-minute demo, is to find and exploit probably the dumbest memory corruption bug ever written by anyone, because I needed a victim that I could write an exploit for really, really fast. But so, does anyone recognize this? I realize that this screenshot is terrible. Being able to read it isn't super important. No one is like cringing visibly, so I'm guessing that none of you have used Fractal's GDB in it. So this is this thing called Fractal G's GDB in it, which is this like monolithic script written entirely in like GDB's kooky scripting language instead of the Python. So you can now embed Python in GDB, which is how this tool works. But before that was possible in GDB 7, GDB had this like Fortran looking scripting language, and Fractal wrote this like genuinely sort of amazing thing. So like from the bottom up, this is like the GDB prompt. This is like a much prettier disassembly of the next few instructions. This is I think the stack, I want to say, and this is some arbitrary heap region pointed to by one of the registers. These are all of the registers, the flags, and then like some more state up ahead. And basically every time the debugger stops, it just like prints out this huge data section, which is like kind of neat in that this is often all of the stuff you want, but not necessarily. And it can be extremely flaky. It turns out that GDB is just like a fickle beast, and the more code you load into GDB, the better your chances of like randomly segfaulting GDB. At the point where you're loading one like a core from one debugger into another debugger to try and like recover your state, you really have to question your life and your choices. And so Snare and I were kind of thinking like there has to be a better way. So anyway, like we basically decided to stop hitting ourselves. And particularly that there's probably actually a good reason that IDEs have shiny point and click interfaces. I wind up interviewing a lot of people at Stripe because I do security things and we'd prefer to hire people with like reasonable intuitions there. And I did a Python interview with someone recently who was like using an IDE, and like I consider myself a connoisseur of fine debuggers, and the like inbuilt Python debugger in like whatever like JetBrains' Python IDE is like fucking awesome now. And I kind of wish that I had that. So instead, we kind of figured that like we would build something a little more modular. And so this screenshot that's also probably really difficult to read, which doesn't particularly matter, is just vanilla LDB. So this is what happens when you load a file, set a breakpoint, and start it. And you get like significantly less information than in Fractal's GDB init. But how could we make this more useful? So this whole talk is just screenshots you can't read. So basically what this is a TMUX session, which I've broken out a little bit. And again, I'm going to hopefully have screenshots you can read at some point in the future. So this is just an LDB prompt with kind of like very little magic in it. And this is a view of the stack. I do have a better one of these. So disassembly the current stack frames, so like the backtrace basically, and then a register view. But the thing that's interesting about this, compared to Fractal's thing, is that these are all TMUX panes. And so the way that I stood this up was I started my debugger, I injected the implant, and then as I decided that I was interested in some new piece of state, I split off my TMUX session and kind of created a new view inside of it. And so architecturally, Voltron looks something like this. So basically, you have the debugger itself, which has this RPC kernel written in Python injected into it, which very, very deliberately has as little code as possible in it, because crashing GDB and LDB is like super easy. We figured the less code that we can stick in there, the better. And then it has two front ends. One is this thing that we call RPC, which is a JSON API that just sits on a Unix socket. And very recently Snare shoved an HTTP API on the side of it. We mostly built it, or well, Snare pretty much entirely built that one as an experiment to see if it'd work. It turns out it does. I honestly sort of haven't played with it, but I fully believe that it exists. I would love for someone to build like a shiny front end for this in the browser. We got as far as like a working register view and then kind of lost interest in it. But the RPC endpoint is extremely well documented, works really well, and has a bunch of like neat features. Like for example, if you're writing code that runs inside of the debugger, you have to be incredibly careful about what you do with threads. GDB has this sweet bug where, in spite of the fact that like technically it should be safe because of Python semantics, if you try to access any GDB internals from a thread that isn't the main Python thread, in spite of the fact that all the Python threads still back onto a single machine thread because of the GIL, it might just randomly crash and everything you know and love is gone. And we let you work around that because you can have external processes kind of like smashing on this RPC API as much as they want. And we've gone through the ridiculous legwork in GDB land of making sure that only accesses, we kind of had this like worker on the main thread that services actual GDB internals so that you can safely do whatever the hell you want without destroying everything you know and love. So kind of quickly stepping through the views that this is nearly readable. Sorry. The story of my life is every time I give this talk, the projector is very, very low resolution. So this is the register view. There's nothing tremendously interesting about it. Probably the most interesting thing is that it shows you the registers that have changed in red, which is really convenient if you're just like stepping through a program really, really quickly, trying to work out what's changed. Just show of hands, how much of what I've said has made any sense so far? Yes! Good times. Sorry, everyone looks a little bit blank, but it's also like 9 o'clock in the morning, so it's hard to say why. Cool. All right, apples. I really like ducks, and so it was just too perfect to have a duck stacking picture. That duck on the top is a badass. Anyway, so then we have the stack view, and this is also a little bit difficult to read, but kind of more interesting, so I'm going to talk about it a little bit. So basically what this has done, if you've done this a few times before, you probably recognize the huge block of A's that is probably a sign of some arsehole putting a fuck ton of A's there to see whether or not something's going to crash. But this stack view is actually a little bit better than Fractal's in that it also makes an attempt to dereference whatever it finds in memory. So for every word-aligned value, it has a look to see if there's like a string literal at the other end, in which case it'll print it. So this is like the MFP cluster that sits at the start of the stack, or just underneath the stack. It can do things like take function pointers and work out what they're actually pointers to. So these are a couple of pointers to the entry point. This is a function pointer that we're going to overwrite in the demo for great success. So straight away, it gives you like a little bit of extra context in that like values on the stack, you can just kind of like eyeball and know whether or not they're interesting without actually having to like go through the rigmarole of copy pasting or looking them up in IDA or whatever. It'll just like show them to you, which is kind of neat. And finally, it has a disassembler that sucks a little bit less than the internal one. It doesn't do a whole bunch extra, although it will kind of like resolve symbols as best it can. It's syntax highlighted if you're kind of into that sort of thing. But so these are the three main plugins. It also, like, the stack view is a little bit more generic in that technically it's just a memory view. So if there's some interesting region of memory that you found through static or dynamic analysis, you can send up another memory view and say like, hey, I just want to look at this specific thing. But so in the spirit of like having tempted the demigods like a champion last night, I'm going to use up the last 15 minutes of my talk with a demo. So basically, what I've done is I've stood up this like inferior process. Oh shit! Hang on. If I get this exactly right, whatever I type in here will. Hey, this way I don't have to break my neck trying to code while looking over my own shoulder. So what I've done is I've created this like victim program, and we're gonna have a quick look at it. This part I do have to look awkwardly over my shoulder for though. So if you have a look at the main function, you can see a couple of things straight away. And to be clear, like this is designed intentionally to be like not elite as possible. I also had to use a bunch of wacky compiler flags to even make this exploitable because modern compilers don't want you to do this kind of thing. But I wanted to basically show like how you can visually find these bugs instead of just like putting a bunch of A's and then like looking at a call. So you can see that we allocate like 150-ish bytes of stack and that we're passing in like 4K as an argument to read in this call here. So everything is probably going to go really, really horribly. And specifically, you can see that we're loading this function pointer to say hi onto the stack. And so say hi does exactly what you think it would. It loads a string, calls printf. Conveniently, there is also this function called unsafe run, which just passes first argument to system, which is probably something we're interested in. So the first thing we're going to do is grab the address of unsafe run because this thing is compiled without ASLR. So jumping into the actual code dynamically, so we have a victim, we call Voltron start, or init. Oh shit, sorry, I'm glad you guys are on the case. Because I am not. Thanks pal. You call Voltron init, which is the actual thing it asked me to do. So, yeah. Okay, set a breakpoint, start the program, and then we'll actually start having a look at what's going on. So we can stand up a stack view, which will show us the current value, like the current state of the stack. I spent so much time this morning trying to work out whether or not I had anything sensitive in my environment. I don't think I do. To be clear, this also works a hell of a lot better when you can have a much bigger terminal, but there was a battle of wits between readable screen real estate and screen real estate at all when I was trying to stand up my demo this morning. And then for chuckles, I'm going to stand up the register view, which very, very conveniently is cut off, but all the stuff we care about just barely makes it onto the screen. So, sorry, I'm trying furiously to wake up. So, normally I'd have the disassembly view as well, which is just like a little bit prettier in that it, it's like syntax highlighted and shit, that I'm definitely not going to be wasting that screen real estate. So as I step through the program, you can see the registers that are changing. So obviously, every time you evaluate an instruction, RIP changes. In this instance, I just evaluated pushing the old frame pointer onto the stack. So you can see my old frame pointer down here. Can you see my cursor? Yeah. No, wait, because that's on my screen. I get this. Sorry, I'm furiously pointing to shit you can't see. So this is the old frame pointer that is just pushed onto the stack, and you can see that it's changed the stack pointer. And so as we step through, it's allocated a bunch of room on the stack. It's setting up the arguments for this read call. Blah, 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 not super important. And so we step into this call to read. I'm just going to step out and say, like, DerbyCon. So now it's stepped back into the main function, and then as we step over it, it's exciting. Have I broken everything? Somewhere up here it should have said, hi DerbyCon. Demos suck. Let's quickly try that again and see if I can not screw this up this time. So we step through into our call to read, step out, say DerbyCon, and so, sorry, it's very early. So as you can see, it's stuck as string DerbyCon on the stack. Unfortunately, this is kind of too small. Oh god. Trying to work out if I can begin this efficiently to actually... Maybe. Aha! Finally! What a lucky guess. So what I was driving at there is that you can see that it's stuck as string DerbyCon on the stack, and way up here you can see this function pointed to say hi that it's about to invoke. And so as we step through the rest of the program, this call to RCX, this is going to be a really exciting battle between which things we can see. It's about to call RCX. You can, if you very quickly eyeball it, you can see that RCX, this value is the same as say hi off the stack. A few instructions ago it was loaded straight off the stack. And so when we call it, it prints hello DerbyCon. Hooray! So now what I want to do is like instead see what happens if we like hack like it's 1999 and just put a fuck ton of A's in place of wherever it wants input, because that'll probably lead to something interesting. So again, we're just going to step through a bunch of times. I could set a breakpoint, but it's probably quicker if I just don't. So we'll step out of this, and this is cyber hacking, you guys. I saw it on CSI. So our stack has been happily obliterated by A's. Morning, champ. Including specifically that function pointer that was like sitting at the top that we used to care about. And so as we step over more things, it loads our A's into RCX, call RCX, which faults because I don't think anyone mapped a page at 41, 41, 41, 41, 41. Great, we have EIP control. So finally, we actually want to like exploit this thing because, why not? So, oh gods, how does computer even make? So we'll quickly write an exploit for this, and live coding exploits always goes really, really well. So basically what I'm going to do, because this thing is like this really naive victim that I wrote for the explicit purpose of exploiting it, it just calls system with things that you pass it, which is super convenient. So we're going to take the first argument and null terminate it. Then we're going to pad it to word length, because basically if I can actually demonstrate this. So if we start over, step over a bunch of calls until we, and then stick our pointer on the stack. Oh god, that's not how pointers work, Richo. You have to give them as binary data. Whatever. So early. So basically the reason that I'm padding this is because if our data doesn't sit on a word boundary, then when we like basically like stack spray, I guess, because like I know it's going to wind up somewhere in that general vicinity. If we're not word aligned, then our pointer doesn't have the benefit of being A's, which sort of doesn't matter if you slide it. So we're going to make sure that it's aligned to 8 bytes. And so finally, we're going to create padding, which is just padding times A. The second thing we're going to do is take this pointer that we have, this function pointer for unsafe run that we already captured from static analysis, and we don't need an info leak because, like, yay, wacky compiler flags that turn off ASLR. And finally, what we're going to do is dump our shell plus our padding plus we're going to pack our pointer as little endian quad word, and we're going to do this like a fuck ton of times because we don't know exactly where on the stack it's going to wind up, and math is hard. So fingers crossed, if we now run our exploit with like ID and this pointer and pipe it into our victim, it runs out arbitrary code. Hooray! Jesus Christ, wasn't expecting that to happen at this time in the morning. But so if we're interested, we can actually like see that working in the debugger as well. So instead of piping it directly to our victim, I'm just going to stick it into a file. And then I'm going to run our inferior, piping in from a file, and Christ, I hope this is the syntax for it. I have a sneaking suspicion that it is not. Nope. Does anyone remember how to pass arguments to Jesus? Sorry? Sorry, I'm having a massive brain fart and I've forgotten how to redirect input in LDB. Actually, what I'm going to do is take it as rote that this works, and instead just show you some more like cool stuff that Voltron can do for you, because I think that's both more interesting and I have a better chance of getting away with it. I swear I'm a professional. So there is a different tool called Calculon, which is just basically a programmer's calculator. And basically what happens is any value that is like an immediate integer, it unpacks as like hex, decimal, octal. It'll have a stab at trying to interpret as an ASCII string, or it'll give you its binary representation. And this is like cool, kind of neat or whatever, but it's mostly only useful as a mechanism. Often when doing this, you like need to calculate a fuck ton of offsets. And so Snare and I used to spend all of our time copy pasting immediate values from the debugger into like a Python REPL to like do math on them and then copy them back into it. And we kind of figured, or I kind of figured like, wouldn't it be neat if we could pull them straight out? So I added this thing where if you start Calculon and you already have Voltron running, you can poke at the inferior directly. So for example, if you do v.rip, it pulls the value of rip straight out of the inferior and shoves it into your process. And then, for example, if you wanted to grab a large section of memory, you could grab, say, like v.rip. So that gives you... Really? Is there nothing mapped at the instruction pointer? That seems unlikely. I hate demos. I hate my life. I hate all of you. Okay. But so basically, like, maybe a better idea would have been to grab the next, like, 10 bytes of the stack. But so what this lets you do is, instead of copy-pasting values all over the place... No, this really is just furiously broken. Oh, shit, no, I see what's going on. You have to use valid Python syntax, or it doesn't work. Yay! That works way better. And so what you can do is, you can use this kind of in combination with what we already saw, which is that everything's really small now. I think this is about the right place. So if I like shove a bunch of A's onto the stack and then do this again and then don't screw up the math. Oh Christ. What have I done? Where did all my A's go? In any case, you know what? I am just going to give up because I'm terrible at this. The gist is basically that, like, instead of copy-pasting immediates left, right, and center all over the place, you can just, like, have your Python REPL right there, grab the values, and, like, do math on them directly instead of dicking around. So with that, I'm going to stop flailing wildly in my shitty 15-minute demo too early in the morning and answer any questions if you have them. No one? Yeah. Did you open a bunch of GitHub issues about it? Okay, yeah, I think someone did. The Windows story, so to be clear, I talked a lot about how this theoretically supports GDB, and honestly, like, it's mostly Snare and a little bit myself maintaining this thing, and to be honest, the code that we use is the only code that we know for sure even, like, boots, let alone, like, actually works. And so the Windows story is... I would be more than happy to fix any bugs you report. Like, if you show me how it doesn't work on Windows, I will fix them. Whether or not it'll still work in 3 weeks after that, who knows? It turns out that, like, unit testing something that pokes at a debugger, which in turn pokes an inferior process, is just, like, miserable. And so while we've done our best to write some tests, and we, like, sort of know that the, like, RPC protocol pretty much works, and we have reasonable confidence that there is nothing much that you can, like, send on the wire that will crash... kind of like crash the IO kernel. Yeah, supporting other platforms has not really been like a huge priority. So there's a third debugger that it supports, which is VDB, which is like Invisigoth at some point wrote a debugger because that's Invisigoth and that's sort of just why he gets out of bed in the morning. And some rando like opens a pull request being like, support VDB! And we merged the shit out of it and I have no idea if it works. So yeah, I strongly suspect that, like, honestly on Windows, while GDB, like, sort of works inside of Cygwin, I just don't think it's, like, the debugger that you want on Windows anyway. Like, I suspect that the thing you want is, like, Ollie or Winbag, but please do open an issue. If nothing else, it'd just sort of be funny to have this working at some point. Yeah, sorry, this is a really long-winded and ultimately unhelpful answer, but I'm sort of asking you to stop hitting yourself. Anything else? Amazing. No one asked me why I didn't use radar. That's normally when I do this, the first question is like, have you heard of radar? Yes, I've heard of radar. Thanks for having me. Feel free to like grab me later and ask any questions.